The report is devoted to prediction of remaining lifetime of the mold for the composite manufacturing. The report is presented by a group of scientists from Beketov National University of Urban Economy in Kharkiv, Ukraine, and National Aerospace University, Kharkiv Aviation Institute, Kharkiv, Ukraine. Performance capabilities of the structures made of polymeric composite materials depend on the accuracy of manufacturing of the part contour. In order to give the part the specified contour, it is necessary to ensure the constancy of the shape and dimensions of the tool throughout the period of their operation. Currently, polymeric composite materials, PKM, are used in many industries. In order to obtain a predetermined contour and geometry of the composite structure, it is necessary to manufacture the molding tools which ensure the structure of regulated quality throughout its lifetime. The choice of optimal parameters of the molding tool at the stage of the designing with a view to obtaining high-quality parts at minimal cost required in integrated approach. In the process of manufacturing of the structure of PKM, it is necessary to ensure the required physical and mechanical characteristics, unity of the structure, as well as the given shape and geometry of the part. The mechanism of lifetime reduction in the composite shaping surface of the tool is different from that in the metal one. In the course of repeated temperature load, stability of the physical and mechanical characteristics of the PKM is lost. However, despite serious developments in the area, the short lifetime of both metal and composite molding tools is recorded in the production practice. And this is due to the fact that in the course of searching of more convenient, lightweight, and uniformly heated structure of molding tools, thin weld frame and composite solutions are usually developed the optimal parameters of each body on critical ones. There are many methods for increasing the lifetime of the molding tools. However, a common drawback of their method is the consideration of a uniform heat supply from the side of the shaping surface of the tools when solving the heat conduction problems. So, the purpose of this work is to develop of methodology for determination of the main parameters of the shape-generating molding tool from the condition of ensuring its stiffness in the molding process at a given surface life. The research tasks are showed on this slide. Technological process of PKM product molding consists in giving in a non-reversible shape with the use of shape-generating molding tools throughout polymerization of the binder at the certain temperature and pressure, varying in time. When the temperature in the autoclave rises, PKM package and shaping surface of the tool begin to deform. Due to the difference in their coefficients, PKM tends to move relative to the shaping surface. We assume that the friction force is sufficient to ensure that PKM does not slip relative to the shaping surface. To determine stresses, we consider the PKM plus shaping surface system as a layered shell obtaining a temperature increasement. This slide presents a computational model for this research. Deflection of the unsupported part of the molding tool is determined by solving of the problem of thermoelasticity of multi-layer shallow shell with the use of the Reed-Timoshenko variational approach. Displacement of the point of the shaping surface were presented as the functions of the variables x and y. Unknown coefficients A, B, C with index I determined from the condition of the minimal total potential energy for the system. Deformation and curvatures of the initial surface of the shell associated with displacement by the following dependencies. Condition for the minimum of the potential deformation energy will be realized by the setting to zero of all derivatives of the total energy with respect to the coefficients of the polynomials. Stresses in the shaping surface are determined as based on the obtained computational dependencies. It is possible to estimate the degree of impact of the geometric parameters and physical and mechanical characteristics of the molding tools and molded composite package of its lifetime. Some words about results. We consider the tool with the shaping surface of thickness delta and dimensions of sides A and B, the shape of which is determined by the curvature coefficients K1 and K2. Here and below, the figure corresponds to the number of the material given in Table 1. Figure 2 shows the dependencies of the lifetime of molding tool N on the thicknesses. It's figure A. This graph shows that thicknessing of the shaping surface leads to the increase in value of the lifetime for any materials. Figure B shows the dependencies of the lifetime of molding tool and of its shaping surface delta. Presents the dependencies of the values of lifetime of the square molding tool on its dimensions and the thickness of shaping surface equal to 1 millimeter. However, when dimensions of the molding tool are increased while maintaining the thickness for the shaping surface at the same physical and mechanical characteristics of the material of the shaping surface, its lifetime is decreasing rapidly. The value of the lifetime of the molding tool depends significantly on the special shape of the shaping surface. In figure 3a, it can be seen that with the increase of the radius of curvature R of the composite product, at least on one side, significant increase in the lifetime for all presented materials is observed. Figure 3b shows the dependencies of the lifetime for the composite shaping surface of the tool at various angles of symmetrical line of the shaping surface. Figures 4 and 5 shows the change of the lifetime of the molding tool after changing of the angle of reinforcement of the manufactured composite part. This figure presents results for the value of the lifetime of the molding tools made of woven glass fiber reinforced plastic and for carbon fiber reinforced plastic on the angle of reinforcement of the molded package of unidirectional carbon. These figures present results for the value of the lifetime of aluminum and steel molding tools of the angle of reinforcement of the molded package of unidirectional carbon. Finally, the following conclusions can be made. Main ways to enhance the lifetime of shape-generating molding tool is to increase the thickness of its shaping surface and reduce the cell size by introduction of the reinforcing ribs. Shaping surface of the shell-type tools has a long lifetime compared to molding tools with the flat shaping surface of equal dimensions. Changing of the material or structure of the molded product requires the check for conformity of the lifetime of the molding tools already designed. Based on the obtained result, the method for increasing the lifetime can be developed for the mold for the composite manufacturing. Thank you very much for your attention. The report is over.
Good afternoon, dear colleagues. We would like to bring to your attention the results of a study conducted jointly by the team of Kharkiv National University, Kharkiv Polytechnic Institute, Department of Integrated Technologies of Mechanical Engineering, named after Simco, Ukraine, and Miskolc University Institute of Manufacturing Science, Hungary. The topic of our report is finite element simulation of diamond grinding. A few words about the relevance of research. Despite the rather long and proven use of diamond grinding as a finishing method to obtain high-quality products for critical industries, the possibilities of these technologies are far from being exhausted. The efficiency of diamond grinding of difficult-to-machine materials is determined by complex and interrelated processes of controlled micro-destruction in the contact zone, which largely depend on the stress level in this area. When optimizing the stress level in the local cutting zone in order to increase the efficiency of grinding, it is necessary to take into account the characteristics of all elements of such a complex system: the diamond wheel structural elements, bond, diamond grains, their size and concentration, the metal phase in the grains, and properties of the process materials. The influence of technological factors of grinding should also be considered. In the system bond, diamond grain, metal phase, process material, the elements, the properties of which can be varied over a wide range are the concentration of diamond grains and the type of wheel bond. Therefore, the main attention was paid to the role of these elements. Using experimental methods to solve this multi-parameter problem is laborious and expensive. In this regard, an urgent task is to develop a methodology for calculating the predicted level of equivalent stresses in the diamond wheel process material system for controlling mutual micro-destruction of systems elements, providing maximum grinding performance and reducing the consumption of expensive diamond grains. Research tasks included the creation of models for static and dynamic simulation, considering the influence of characteristics of the system's elements on the level of equivalent stresses in the grinding zone, selection of the criterion of controlled destruction of the elements of the grinding wheel, analysis of the role of bond and diamond grains concentration as one of the key factors in the grinding efficiency. The next slides are focused on the research methodology, which consists of two directions: static and dynamic modeling. The static modeling research methodology was based on the use of the SolidWorks simulation. The main influencing parameters were the concentration of diamond wheel grains, the size of the diamond powder, size of grain wear zones, embedment depth of grains in the bond, composition, size, and shape of the metal phase in the grain, and bond porosity. The research methodology for dynamic modeling was based on the use of ANSYS and LS-DYNA software packages. The force and cutting speed values were similar to the actual grinding process. As initial data, concrete grid size, bond types, and types of processed materials were chosen. The next step is the results of our research. Static modeling was used to solve two problems. Firstly, analysis of the distribution of equivalent stresses in the elements of the research system, and secondly, study of the effect of grains concentration, which was 25, 50, and 100%, and the type of wheel bond, trade grade ceramic and research grade glass ceramic, on the destruction intensity of diamond wheels elements. It is shown that the maximum equivalent stresses are observed in contact zones of diamond grains with the bond and the processed material. Stresses in diamond grains are localized mainly around the metal phase. As criteria for the controlled destruction of the elements of the diamond wheel, the following were chosen. For diamond grains, the relative volume of grains where the equivalent stresses exceed the ultimate tensile strength of diamond grains, considering their grade and size. For a wheel bond, the equivalent stresses exceed the corresponding ultimate strength value, and the volume of their distribution is more than 20%. The results of the calculation showed that an increase in the diamond grains concentration of the diamond-bearing layer causes an increase in the destruction criterion for both types of the studied bonds, while the destruction criterion for the diamond grains decreases for all studied materials, sital and cemented carbide. The intensity of destruction of the bond and the value of the equivalent stresses arising in each with the change in the concentration of the wheel's grains are associated with the physical and mechanical properties of the bond, mainly Young's modulus. For example, in grinding wheels with ceramic bond, an increase in the concentration of the grains over 50% causes bond destruction, leading to the premature removal of diamond grains from the wheel working surface and to an increase in their specific consumption. In grinding wheels with research-grade glass ceramic bond, an increase in the concentration of the grains over 25 to 50% caused destruction of the bond. Increase of grains concentration up to 100% causes the partial micro-destruction of both system elements, grains and bond, and creates the preconditions for renewal of the cutting surfaces of the diamond grains. The calculation showed an increase in equivalent stresses in the studied bonds, ceramic and glass ceramic type, with an increase in the concentration of diamond grains from 25 to 100%. Equivalent stresses in the ceramic bond exceed the ultimate tensile strength for all studied grains concentration in the wheel. Equivalent stresses in the ceramic glass bond reach the corresponding tensile strength level only at 100% grains concentration. Based on dynamic micro-level modeling, the stress distribution diagrams in the complex system diamond wheel, difficult to machine material during grinding by a group of grains at a certain cutting speed were obtained. The dynamic changes in the stress values were determined. Timing charts of the volumes of destroyed grains and machined materials were presented. The ratio of the removed materials volume and volume of grain destruction was proposed to estimate the specific consumption of diamond grains. Grinding performance was estimated as the volume of the destroyed process material per unit of time. And finally, the following main conclusions and recommendations for possible practical use of the results. The factors determining the intensity of mutual controlled destruction of the diamond wheels elements during grinding were identified. An increase in the Young's modulus of their bond leads to an increase in equivalent stresses in the contact zone of the wheel with the process material, and as a result, it contributes to an increase in the efficiency of the process. Limiting the concentration of diamond grains in the diamond-bearing layer to 50% increases the possibility of the machining and reduces the cost of the diamond grinding wheels. Some recommendations can be given for optimizing the technological parameters of grinding, the characteristics of diamond powders, and the ceramic and ceramic glass bonds properties. All these factors ensure the effective grinding in the self-sharpening mode with minimal loss of grains. Thank you for your attention. Best regards, research team.
Good day. My name is Oleg Onisko, Ivano-Frankivsk National Technical University of Oil and Gas. And we have in this presentation named as impact of the tool flanks clearance angle on the pitch diameter accuracy of the tool joint taper thread. Introduction and major challenges of Mahalar works. Today, the urgent problem of the energy industry in the world is the development of classical and development of new, including environmentally friendly and energy-saving mining technologies to increase the productivity of oil and gas wells. Successful implementation of such technologies requires the improvement of mining equipment and tools, which is characterized by the presence of a large number of threaded, cylindrical, and tapered connections. Major challenges. Within the technological support of high performance and high precision manufacturing of taper thread between the design of the threads and the geometry of the cutting part of the cutting tool, often the correlation between the angle of the rise of the thread and identical to it the value of the clearance angle of the cutting edge is used. At the same time, one of the most influential indicators of the accuracy of the obtained thread is the accuracy of its average or pitch diameter. Therefore, the influence of the technological design and operational factors on the quality and the accuracy of the threads in general and its average diameter, so pitch diameter, in particular, should be investigated. Research tasks. Research tasks. Theoretical investigation of the influence of the technological factor of time, the angle of inclination of the cutting edge on the deviations of the pitch diameter. The next, creating an algorithmic application to calculate the accuracy of the obtained pitch diameter. The next, determination of their percentage contribution of the influence of the angle of inclination to the permissible deviation of the pitch diameter. Research methodology. Research methodology consists from the next materials. This here scheme to calculate the value of the deviation of the obtained profile of the cannulate surface from the specified due to the standard profile of the thread. This formula obtained by our researchers before in the XZ plane of the actual section of the thread, whereas y is 0, is realized in the analytical way as a convoluted helical surface, but taking into account the influence of the flank clearance angle lambda. Scheme of the standard tool joint taper thread with Cartesian coordinate systems. Based on the APA 7 standard, the scheme of the profile of the threaded tool joint connection of the pin box in the ZX coordinate system with their indicated pitch diameter is made here. Theoretical investigation of the obtained pitch diameter accuracy. Scheme about standard tool joint taper thread and cutter tool model with coordinate Cartesian system, and the scheme of the standard tool joint taper thread and the cutter tool model with coordinate system 2. Comparison of the threads of the pin box, taking into account of the offset of their profiles relative to the standard. From figure here and here, it is clear that the method or the model of pitch diameter of the taper thread based on the definition pitch diameter. Definition R. The basic thread pitch diameter is a diameter with where the thread thickness is equal to the space between trace and root. Whereas flats at the top of the bottom of the thread are the same, the pitch diameter will coincide with the middle of the sloping side of the thread. Results. Results of problem is using the program calculated are shown in the form of tables. In the left column, the coordinates x are included, and in the columns Z1 and Z2, the corresponding coordinates are the standard profile and the profile obtained by the cutter within corresponding flank clearance angle are indicated. Column Z2 minus Z1 shows the point-by-point mutual deviation of the profiles. Program calculations. Calculation of the profile of the thread NC23 as the following values of the flank clearance angle of the cutting edge lambda 2 and 6 degree. So we take into account this mode. The next table, calculation of the profile of the thread NC50 with clearance edge lambda equal 1 degree, and the NC77 calculation profile lambda 0.5. Here and here is our main result of our conclusions. Obtained results. The analysis of the obtained results shows that the function dependence of the change in the pitch diameter of the step size or the height of the fundamental triangle is not detected, but it is absolutely clear that with increasing diameter of the thread cone smaller base, the magnitude of the change and its pitch diameter decreases from 0 to 0.0. So it is the same that 8 persons to 0 persons. Conclusions. The theoretical researches and algorithmic prediction calculations of accuracy of process of threading on their basis have shown the following. The main tool factor that affects the change in the pitch diameter of the taper thread is the value of the flank clearance angle at the cutter, because with its increasing, the pitch diameter increases too. The second, the increase in the pitch diameter of the taper thread functionally depends on the diameter of the conical base. An increase in this diameter leads to a decrease of the magnitude of the change in the pitch diameter deviation and vice versa. The values of the average diameter, so that mean pitch diameter of the taper thread of the largest size, do not depend at all on the value of clearing angle of the cutting edge of the cutter. Thank you very much for your attention.
Good afternoon, conference participants. Your attention is invited to the presentation of the article Improving the Efficiency of Fine Boring of Stepped Bore with Large Difference in Diameter. Team of authors: Doctor of Technical Sciences Alexander Argiyan, Doctor of Technical Sciences Gennady Aborsky, Doctor of Technical Sciences Vitaly Ivanov, PhD Anna Bolonyuk, and PhD Vasil Kolesnik. The second and third slides show Introduction and Major Challenges. When studying the dynamic influences observed in finishing boring machines, researchers focus on study of oscillations of cantilever boring bars mounted on the spindle heads. The relative movements of the cutter and the workpiece, static and dynamic, determine the vibrations that occur in the closed dynamic system of the machine and negatively affect the achievable accuracy. An analysis of the round hole patterns of bored hole shows that vibrations are a factor that determines the errors in cross-sectional shape and machining accuracy. Cantilever boring bars, providing high productivity when boring smooth holes by special bore finishing machines, are widely used. However, it should be noted that it is often necessary to bore stepped holes. Thus, according to our estimates, 21% of fine boring machines are equipped with two-step boring bars, and more than 10% with three-step boring bars. We consider that the insufficient use of multi-step cantilever boring bars is due to the lack of the necessary substantiations of the methodology for designing special designs of boring bars and multi-cutter heads. One of the main limitations on the use of cantilever boring bars is the increased bending compliance of the cutter, technological compliance, which leads to a decrease on their vibration resistance. At the same time, cantilever boring bars also exhibit significant variability of technological compliance during rotation due to changes in contact conditions in the bearings of the spindle support devices. The fourth and fifth slides present aim and research tasks. The research aim is ensure the same wear of the cutters at different stages of the boring bar. Research tasks: provide different speeds and the same linear cutting speed at different steps. To study the effect of fluctuation on the quality of processing with boring two-stepped holes with the same recommended cutting speed. The sixth, seventh, and eighth slides present research methodology. In mental working practice, it is often necessary to bore stepped holes, for example 2 or 3 step, with a significant difference in diameter. In this case, the optimal cutting speed is determined based on the material and diameter of the workpiece, the material of the cutter, the depth of cut, feed, etc. For example, When boring holes diameter 100 mm and 50 mm in piece of medium carbon steel, when cutting with two simultaneously operating cutters, the recommended span cutting is equal to 200–250 meter on minutes for carbide tools. To ensure the same recommended cutting speed for steps with different diameters, the speed of each step should be different. For example, the rotational speed of the step with a large diameter should be half of the frequency of a step with a smaller diameter when boring two-step holes with diameter of 85 mm and 45 mm. The task was implemented when boring with a special boring bar, the design of which is shown on the 8th slide. The fundamental difference between the design of a special boring bar and all known designs is that a step with a smaller diameter 1 is the base one, on which a step with a large diameter 2 is fixed and has groove 7 for the belt drive. This solution ensures the same optimum cutting speed in both steps. The principle of operation of a special boring bar is that cutters 5 and 6 work simultaneously upon cutting, while the lengths of steps 1 and 2 correspond to the lengths of the holes to be machined. A step with a smaller diameter 1 rotates at a speed that is equal to the rotational speed of the spindle 3 and is equal to the optimal cutting speed for specific machining conditions. To ensure the same operating conditions for cutters 5 and 6, the step with a large diameter 2 is rotated by additional drive, while the ratio of rotation speed of a step with a smaller diameter 1 and a step with a large diameter 2 is inversely proportional to the ratio of their diameters. The required gear ratio is set using pulleys 13 and 18. From the 9th to the 13th slide is presented results. Figure shows oscillograms of vibrations of a special boring bar when two cutters operate simultaneously. The vibration amplitudes were determined from the oscillograms and compared with the vibration amplitudes of a conventional two-step boring bar in Figure B. On the 11th slide are presented round diagrams of bored two-step holes with conventional and special boring bars. Rudness deviation measurements were performed on a tele-round measuring machine, Japan, based on the processing of rudness charts of bored holes. 12th slide shows diagrams of the average values of deviations from the rudness of the holes when changing the number and sequence of cutters. It can be seen that the value of deviations from circularity during the operation of the second cutter doesn't differ significantly. However, in the case of the operation of the first cutter mounted on a conventional boring bar after 10 boring operations, these deviations increase significantly due to wear of the cutting blades. In this case, deviations from circularity when boring with a special boring bar change slightly. The 13th slide shows the dependence of the average values of the surface roughness of the holes on the number and sequence of the cutters. As you can see on slide 13, after 10 borings with a conventional boring bar, the roughness at diameter 85 mm deteriorates significantly. At the same time, the surface roughness doesn't particularly change when boring with a special boring bar. The 14th and 15th slides present conclusions. The experiments show results that characterize vibrations, surface roughness, deviations from rudeness, and wear of cutting blades. The results obtained during boring with a conventional boring bar and a special boring bar that ensures the same linear speed of the cutting blades at different steps were compared. In the first case, the cutting speeds on the cutters differ by a factor of 2, and the recommended cutting speed is set on the second cutter, which is farthest from the spindle head. Stepped holes with the same step lengths were machined. This ensured the average values of the influence coefficients that determine the transfer to disturbances between cutters during their joint operation. It should be noted that the comparison of the results is characterized by insignificant changes in the vibration amplitudes. The wear values of the cutting plates during the transition from boring with a solid boring bar to boring with a special boring bar on the second cutter are practically the same and are within the range of 7-8 micrometers on 103 meters. The lower wear value corresponds to a conventional boring bar. The wear values on the first cutter, a step with a large diameter, for such boring bars are different. The relative wear is 13-18 micrometers on 10 to the third power for conventional boring bar and 8-9 micrometers on 10 to the third power for a special boring bar where measurement error is 0.5 micrometers. The paper devotes to possibility of fine boring of stepped holes with a large difference in step diameters with special boring bars providing the same recommended cutting speed. Due to such boring, the wear of the cutters are practically the same, which leads to an increase in boring accuracy, the stability of the roughness value and deviations from rudeness, as well as boring at one setup, which makes it possible to reduce the time for adjusting the cutters. Boring of whole steps at the same cutting speed is ensured when designing special boring bars, taking into account the geometric characteristics of the part, that is, lengths and diameters of the steps, the material of the workpieces, as well as cutting conditions. Thank you very much for your attention.
Dear friends, my name is Vadim Stupnitsky. I am a professor, head of Department of Lviv Polytechnical National University. The subject of this research work is simulation studies of high-speed machining. High-speed machining is the way to significantly increase the productivity and an additional tool set to improve the machining surface quality and reduce cutting strength. It's because the contact time of the tool with the machined material is so short and the rate of chip formation is so high. Then the chip removes more the heterogeneous lies in the cutting zone, and the workpiece and tool do have not time to head up, which is effective for the cutting process. At certain cutting speeds, head extraction begin to decrease, accompanied by reduction of cutting load, as can you see on this slide. The chip tool contact time is so short and the cutting speed is so high that most of the head generated in the cutting zone is removed with the chip, and the workpiece and tool can't head up. It has a beneficial effect on both the force and stress-strain state process taking place in the chip formation zone. Generally, blade machining of plastic material produces grain chips. Plastic deformation occurs and it contributes to the efficient cutting of the materials. It's observed the friction process between the chip and the tool rake face and between the workpiece and the relief face of the tool. In high-speed machining, the coefficient of friction decreases as the speed increases, as you can see for this figure. This is due to softening of the machined material in the cutting zone, in some cases with the appearance of the liquid layer. The aim of my research work, the primary tool of the described study is the deformed 2D software. The functionality of this software allows to create the simulation model of high-speed machine. Such basic research parameters as speed and tool design significantly influence the elastic deforming state and the thermodynamics parameters in the cutting zone. And allow to creation adequate simulation model of the high-speed cutting processes. There is the same task for study to study the influence of force and thermodynamic processes of cutting toolware during the high-speed cutting machining. Research tasks are for fastly. The simulation of high-speed cutting processes is very complex because the dimensionality of the modeling problems increases tenfold compared to medium-speed cutting process. Therefore, the solution of this problem is characterized primarily by methodical novelty. The proposed approach enables a comparative analysis of force and thermodynamic process occurring in the tool and chip formation zone during the high-speed cutting. Secondly, the results of cutting force dynamics and thermal loads of different cutting speeds are described in this study. Thirdly, the analysis of tool wear rate for different geometrical design of the cutting edge is current up and fast. And fourthly, the last task. This is to study the phenomenon of excessive grooves of cutting force with the increase of machining speed. The used research method is to analyze simulation results in the rheological modeling system, simulation system in system deformity. This system is a multi-purpose finite element analysis program intended to solve a 2- and 3-dimensional dynamic linear problems to solid-state deformation mechanism and problems associated with this process. There are different possibilities of this system can to decide some problems about strain, stretch, strain rate, the deformation, thermodynamic state during the machining in different conditions of cutting. Scientific design. The results of simulation study of the high-speed cutting power parameters are shown in this slide. There are, for comparison of the processes with usual the medium speed machining and high-speed machining, we can show the results for simulation in cutting force about for speed 100 meter per minute and for speeds 800 meter per minute and 1600 meter per minute. And there are different color. The analysis of graph dependencies show that that at speed 1600 meter per minute, the cutting force is approximately 17, higher than the magnitude obtained in simulating the cutting process at speed 100 meter per minute. If comparing these values with the value obtained in speed 100 meter per minute, this difference over 23 and 30% respectively. One of the main characteristics of cutting process is the temperature. The functionality of the deformed 2D software made it possible to investigate that value, which is shown on this slide. You can see there with 100 meter per minute and 1600 meter per minute, this value will be about 1150 degrees Celsius and 1400 degrees Celsius respectively. This is very more than for 500 and more than 800 degrees is higher in usual speed. That the special requirements for thermal resistance of tool must be ensured. It is possible to explain the obtained result to temperature growth by such heat sources is cutting zone. We can to explain fastly. The internal friction between the particles of material they are being shared as a result of deformation during the chip formation. Sadly, the friction of the chip against the rake face of the tool, friction of the cutting surface and the machine surface on the relief face of the tool. We studied the different type of tools for to analyze what we have to use the different rake face of tools and influence for this designing decision for temperature and for tool wear during the high-speed machining. You can see for about cutting force the difference for using tools type for speed 800 meter per minute is about 8%. And for speed 1600 meter per minute, the difference is more and is about 14%. And if we said about if we studied the difference of temperature, the difference for these types of tool for machining with for machining with speed 800 meter per minute is not more. This is about 10 or 11% about. And very important our study for using this design fastly for wear rate of tool wear rate. And you can for this figure you can see the difference with speed 1600 meter per minute, and usually this difference is about 15%. It's a very great difference, and this is a very great result, good result for this investigation. And you can see the zone for maximum wear of rake face concentrated in point where the speed for sliding speed of chip according to the rake face of tool is greatest, and therefore in this point we have a maximum of wear. And accordingly for this investigation, we can to propose the different design of tools, and we can see to the tools where depths are different things. And about conclusion, you can see the conclusions for this study, and I can't do time to explain exactly these conclusions, but I want to see, and I can to answer for the question for this study. Thank you very much for your attention.
Good afternoon. My name is Olga Zaleta, and first of all, I would like to thank very much the organizing committee for the opportunity to take part in this esteemed scientific event, and also congratulate all participants. Please let me acquaint you with the results of the work carried out by scientists of Lutsk National Technical University and Slovak University of Technology. Thus, the topic of our work is investigation of the surface layer hardness when grinding sintered porous workpieces. The rapid development of technology in general and powder metallurgy in particular has made the geometric shapes of workpieces more complicated. The accuracy of the executive dimensions of machine parts have also increased. One of the types of mechanical processing of sintered powder materials is abrasive machining. It provides the highest accuracy and purity class of machined parts. Besides, its physical and chemical phenomena differ from the usual processing of metals by cutting. Abrasive machining makes possible to produce many parts such as brackets, handles, holders of metalwork, assembly, tools, etc. Sintering is one of the most important industrial techniques for optimizing the capabilities of different materials. The processing of sintered metal differs from compact steels due to the heterogeneous microstructure and porosity. Therefore, the main task in grinding parts of porous sintered materials is to form the necessary properties of the surface layer. The processing of such materials should improve the structural features of the material which were formed in the process of the manufacture of the workpieces. The main task of the research is to study the influence of transverse feed, cutting speed, and porosity on the hardness of the surface layer and its compaction, which affect the operational parameters of the part. In poster, you can see right now the initial data for the experiment is described. The iron powder was pressed using a high-pressure chamber. An elastic shell was used as a matrix. For the method of mechanical processing of samples, dry grinding was chosen. Also, it was determined the kind of the equipment, specific pressure force for obtaining wanted porosity, sintering temperatures, hardness, and the effect of cutting depths for different cutting modes on the compaction of the workpiece surface layer. This poster shows what modes of grinding were adopted. It applies to the values of such parameters as depth, the speed of the workpiece, cutting speed, transverse speed, and grinding width. And now I am going to present to your attention the results of our research. In this poster, it is presented Figure 1 and Figure 2. Figure 1 shows the dependence of the compaction of the depth of the surface layer. As we can see, the compaction of the porous sample decreases in the case of increasing the depth of the surface layer, and at the same time, porosity increases. That is presented in Figure 2. Next poster also contains two graphs. They give the detailed information about the dependence of the thickness of the compacted layer on the speed of workpiece and transverse feed. It was observed that in the case of the decrease in the transverse feed and cutting speed, the thickness of the compacted layer increased. For the samples with a porosity of 32%, the thickness of the compacted layer is 100 micrometers more than the samples with a porosity of 24% for the same processing modes. Next step is studying the effect of processing speeds of workpiece speed and transfer speed on surface hardness. To do it, we have chosen an initial workpiece with porosity 24% and microhardness HB46. The obtained results described in Figure 4 show that the surface hardness of the sample after processing with speed 4 meters per minute increased almost twofold. It is about HB80. Further increase in speed gradually reduces the surface hardness. In particular, for speed 12 meters per minute, the hardness is HB40, which is about 2 times less than the surface hardness for processing with speed 4 meters per minute. From the Figure 5, it is possible to find out that the hardness of the surface layer is significantly affected by temperature dimensions, which directly depend on the transfer speed of the treatment. Increasing the transfer speed raises the temperature in the grinding zone and reduces the hardness of the workpiece. It is important to note that feed and speed affect the thickness of the compacted layer. Reducing these processing parameters will increase the compacted layer of the workpiece. Figure 6 shows obtained dependencies of hardness of the steps of the defective layer based on a series of experiments with transfer speed 0.1, 0.3 and 0.5 mm per stroke. Presented data means that with increasing the depth of the defective layer, the hardness gradually decreases and acquires the value of the surface hardness of the initial workpiece. The study proves that to ensure high hardness of the surface layer, it is necessary to use minimum transfer speed. Any increase of the transfer speed reduces the hardness of the surface and reduces its wear resistance. Therefore, it is time to sum up all that has been said and shown. First of all, it was found that a result of grinding sintered powder workpieces is the compaction of their surface layers. The thickness of the compacted layer decreases due to increasing the speed of the workpiece movement, reducing the time of action of the grinding wheel on the surface, narrowing of the plastic deformation zone. The thickness of the compacted layer increases due to increasing the transfer speed, decreasing the depth of the cut layer. Testing the workpiece by grinding indicated that this treatment increases the micro-hardness of the surface layer twofold. Treatment with minimum allowable transfer speed increases the hardness of the surface layer, and the increase of the transfer speed causes the decrease of surface hardness. The optimal modes of grinding processing of porous workpieces are the next. Transfer speed is about 0.3 mm per stroke, and the workpiece speed is about 5 meters per minute. The obtained results encourage to study the plastic deformation of the surface layer and residual stresses of the first kind, which are the important factors influencing the surface quality, fatigue strength, and wear resistance of parts. Thank you very much for your attention. I wish all participants great scientific achievements and hope to meet you again next time.
So thank you. Thank you very much for all presentations, all the presenters. Now it's time to throw some questions and answers for summarizing this session. So let me start for the first presentation. Just to remind, that was the presentation about prediction of remaining lifetime of the mold for the composite manufacturing. The presentation was made by Tetiana Nabokina. The main goal of this presentation was to develop the model of the temperature stress strain behavior of the tools on the process of composite products. So do we have any questions for this presentation? No, I don't receive any information from the chat, but I can see that Tetiana Nabokina is with us, is present. Yes, I'm right.
I'm here. I'm greeting
Yes.
participants.
Thank you. So if you have any questions on chat, I would like to ask you just very short, simple questions, because you are mentioning about the prediction of the mining lifetime and you are developed the model. And all the time when we are talking about prediction of the developed model, we are talking about the accuracy of the models and the predictions error. Can you tell us if you have assessed the accuracy of this model and what was the prediction error?
We analyze different ways to define the lifetime of the mold, and we accepted that the lifetime depends on the numbers of molding of cycles, and considered the system as a multi-layer shallow shells, where one layer is the molding and second layer is the PKM products. And we receive some theoretical results which have very good agreements with the known data. And we can be noted then main results to enhance the lifetime of the molding is increase the thickness of the shaping surface, reduce the cell size by introduction of the reinforcing ribs, use shaping surface of the shell type tools. It's obvious and confirmed mathematically. And changing of the material of the products requires the check of the lifetime of the molding tools which already designed.
Thank you very much for your answer. I like this results very much. So congratulations and good luck for the next step of your research. Thank you. And let's go to the next presentation. Just to remind, it was the presentation on the title Finite Element Simulation Diamond Grinding. And the presenter was Larissa Pupan, as also the main goal of the research was to develop the methodology for calculating the predicted level of equivalent stress in the diamond wheel processed material system. Do we have a presenter of our session?
No speaker in the chat.
No speaker is not here, but okay, so I just had asked, maybe I can send a question to the corresponding author, because the results were very interesting. I like it very much, but it's all simulation. So I would like to ask about the implementing these results in practice, mainly in the industry, because it's always very interesting to think, to know about this, how it was, how is the further next step of the research. So congratulations, all the authors of this presentation. And let's go to the third presentation, impact of the tool flank clearance angle of the pitch diameter accuracy of the tool joint wrapper retreat. The presenter was Oleg Onysko. And the main goal of the research was the investigation of the influence of the technological factor of tuning the angle of nucleation of cutting edge of deviations of pitch diameter. Do we have Oleg on chat? No on chat. Okay, because so maybe I can ask the question. So my question was to the authors, did they analyze the average diameters from the cutter rake angle value? But I think I will send the question on the email. Okay, so let's go to the next presentation. I can see that Anna Balaniuk is also not on the chat, but the presentation was very interesting also. Just to remind, it was the presentation about improvement of the efficiency of fine boring bore-stepped holes with the large diameter range. And it was also the linear models and the cutting speed on different steps. So maybe I will not. I will send also the question to the authors on the chat. But my question was because I was interested about the analysis of the surface quality, surface roughness, because the authors have analyzed some indicators, mainly an array parameter. But of course, we have other parameters that we can assess the surface roughness. So I would like to ask about other parameters. So I will send the question on the email. So let's go to the fifth presentation. Do we have the presenter, Vadim Stupnitsky? It was presented by Vadim Stupnitsky, and also this was simulation studies of the high-speed machining. I like this paper very much because it's very close to my topics also. So because there are proposed some changing designing of the cutter in the under the simulation. So my questions I would like to ask, but I cannot now. But I also will send the question to the authors. What about the useful lifetime, and of course of the cost to designing the new cutters, and because of the technological changes of the parameters. So. Let's go to do we have any questions to the paper, this one? Also not. We cannot have any questions. So let's go to the presentation number 6. It was also, we have, do we have?
Dear Katarzyna, Professor Stupnitsky in the chat, maybe he
No, I'm here.
Oh, yes. Professor Stupnitsky is in the chat. Okay, I'm sorry.
I'd like to say that there are problems with...
Sorry.
Yes,
sorry, it was my mistake. Vadim Stupnitsky is also. Have you heard my questions about the cost of designing the new cutters and the useful lifetime of these new cutters?
New cutters, I said in my research, I said not about using the different cutters just in total, but only proof about change the face of this cutter, because we investigated that the highest temperature during the high-speed machining appear in some surface, which this is interesting idea, because the change of appear the highest temperature is change according to the usual theory, and therefore we try to change this surface change only rake phase. Yes. And we investigated about idea for changing to the rate of usual tools, and we received the theoretical result, and just in this time we try to make the experiments accordingly to this work. This is not exactly my work, but it's work of my postgraduate student, and I think that all total result will be to later according to the experimental work. But thank you for this question.
Thank you very much for your answer. Do we have any more questions to the professor? Yes, Professor Vitali. Yes, would like to ask the questions.
No, I just to say thank you.
Thank you.
Thank you.
Thank you for attention.
Thank you. So I think we can go to the next presentation. The next presentation was the formation zones and clarification during the forming broaching. It was presented by Igor Shepelenko, but I don't think that Igor is with us. Yes.
It was not presented.
Yes, but okay. So
Katarzyna, just sorry for interrupting you. The speaker Larisa Pupan is in the chat. You had previously a question to her. It was presentation 7.2.
7.2. Let's go back to the presentation. Hello, Larisa. Nice to. I cannot hear you exactly. Maybe it's only my problem. Okay, thank you very much. Can you hear me, Larisa?
I hear you, but something bad.
Yes, because of the.
But now I hear you.
Okay, because I was talking after your presentation that I liked your presentation very much, and you have made a very good simulation result.
What was the question?
Yes, and I would like to ask you now, because the results are very interesting from the simulations. So I would like to ask you, did you try to prepare some general methodology to implement these results in the industry, in the practice? Because the results are very interesting. Did you try to do it? Or it will be the next step of your research? Larisa?
The next step of our research quality, because two main problems are to have a great efficiency, cost productivity. By the way, I am a specialist in the studying of surface quality by electron microscopy and optical microscopy, so it will be the next step of our research.
So the quality of the surface, yes? Did I heard it well?
Yes.
Yes, okay. So thank you very much that you have answered this question. Thank you again.
Thanks for you.
And good luck for your next researches. And so we can back now for the presentation 7.7. Yes, it was the presentation performed by the Olha Zaleta about the investigation of the surface line hardness when grinding sintered porous workpieces. Yes, it's Olha. Yes, Olha is it was.
I'm here. Nice to hear you.
Nice to hear you, Olha. So do we have any questions from the chat, from the others?
It looks like there are no questions in chat.
So, but may ask you some just very simple questions, because as I thought, I'm always interested to put, because a lot of research results are very good from the theoretical point of view, and we obtain very good results, but I'm always asking about how we can, if we can, of course, on the stage, can implement some of your results in the practice, for example, in the industry.
Thank you for the question. Our results that we had obtained, they can be used during the using the parts that were machined by grinding, and during this process it can there are micro hacks can appear, and these micro hacks can destroy the part during the future, during using in the future. And one of the purpose and one of the aim of our investigation was to obtain such results that we can analyze and understand how micro hacks can appear, and how large they are, and how they can influence on the part during the using. I'm not sure I can sorry for my English. I'm not sure I could explain everything clear, but I tried. Sorry
Thank you very
for my
much
mistakes.
Thank you very much, Fiona. I think that all of us will understand very well. So thank you very much, and good luck for your next stage of your studies or your research. Good luck. That was very interesting. And
thank you very much
again. And let's go for the last presentation, but not least presentation. The last presentation was presented by Tatiana Loza. It was titled Preliminary Abrasive Besting Surface Layer and Quality Assurance of the Toation Coatings or Aircraft Engine Parts. I like this presentation very much because it's connected with my faculty of Mechanical Engineering and Aeronautics, actually for my region here in Rzeszów. So do we have some questions of this for this presentation, sorry?
No questions and no speaker, unfortunately.
No questions, no speakers. So maybe I will contact and authors because I would like to asking about the research of the different blades of the different gas engines. But okay, I will send the question to the email of the authors. So it was the last presentation of our session. So I would like to thanks again all the presenters for this very nice, interesting presentations. Thank you for all the questions and answers. And I would like to finally congratulate the organizers for a very nice event, even though this situation is very difficult in Ukraine. Thank you very much. Thank you, Professor Ivan, for inviting me to chair this session, and good luck all of them, and see you soon. I hope in Ukraine, because this time I should be in Sumy, not here in Rzeszów. Thank you again and see you.
Dziękujemy Pani Katarzyna, że to jest nie tylko do Was, do wszystkich polskich przyjaciół, że za współpracę, za pomoc dla Ukraińców, dlatego, że mamy takie trudne czasy i już mamy więcej naszych przyjaciół i mamy nadzieję, że w następnym roku już będziemy tą konferencję robić, może być w Sumach, może być w innym miejscu, ale tylko w Ukrainie. I zapraszamy.
Dziękuję bardzo. Dziękuję. Oczywiście, jeżeli
bardzo
tylko
miło
będę
było poznać.
Bardzo dziękuję. Oczywiście, jeżeli tylko będzie możliwość, będę robić wszystko, żeby przyjechać do Ukrainy w końcu na konferencję, w której uczestniczę już kilka lat. Niestety nigdy osobiście, tylko zawsze, not only tylko online. So thank you again for your invitation.
Bardzo.
And
Zapraszamy do
I
Lwowa.
promise that it will be the possibility I will come to the Ukraine.
Thank you very much to all participants. Thank you very much to Professor Antosh for your acceptance to chair this session and for your commitment, for your time and your useful comments during this working session. Thank you very much. Looking forward to our next meeting offline.
Offline, yes, in person. I hope so.
Thank you very much.
Thank you, Vitaly, again, and see you. Bye.
Thank you very much.
Thank you.
Dear participants, we will continue our conference. Next session will start according to agenda and will be chaired by Professor Vadim Stupnitsky.
Just 1 minute. Oh, dear friends, I am pleased to welcome you to a new session of our conference. My name is Vadim Stupnitsky. I am chair of this session. I'm head of department from Lviv Polytechnical National University. More of my friends know me, but sometimes appears the new situation when we don't meet. But hello, really, I am very glad to see my friends, my last friends and new friends in our conference. Slavomir, this is one of the best my friends for helping Ukraine. Yes. Oh,
good to see you, Vadim. Good to see you.
See, I'm glad to see you. Same. And I'll be chair of this session. Today we'll have 5 presentations. Be reports following scientific project fast from our Greece, France, surface defects detection on pressure casting on machine learning, exploiting machine vision features. I don't know who will be the presented this report, but I think that we'll have in later. Next from this report will be from Odessa Polytechnical National University and Odessa Military Academy and from Odessa State Agrarian University. This concept knows generating gear grinding optimization. I think that Professor Larsen will be a reporter. Thirdly, the report will be ensuring a quality or conceal mating surface processing by diamond honing from Romania Engineering and University after FZ Yakubov. I don't know who will be, if maybe the Ashraf or Alper.
Ruslan Jamaladinov will be a speaker for this.
Ruslan, yes, will be Ruslan. Next, influence of turning operation on various characteristics of working surface on rolling bearings from Lutsk National Technical University or Wyższa Szkoła Kadr Międzynarodowych Poland. This is in Poland language. And then a high school of międzynarodowych to no nie wiem, oczywiście. And the next report and last report will be a new method of monitoring cutter state in finishing turning of fight materials. My friend Alexander Derevyanchenko from Odessa Polytechnical National University will be reported in this report. The sequence will be first follows. First, we'll listen to the stream in report by report mode. Isn't it? Yes? Next, there will be a question for each speaker, and so I ask to stay turned and the answer for the question. If there are no other suggestion, I will ask our team to start the presentation of reports.
Hello, my name is George Vosniakos. I'm Professor of Manufacturing Systems at the National Technical University of Athens in Greece. I'm going to present to you our paper titled Detecting Surface Defects on Pressure Die Castings by Machine Learning Exploiting Machine Vision Features. My co-author is Zoe Papagianni. We are, as I said, both from National Technical University of Athens Manufacturing Technology Lab. Now, the domain we deal with is pressure die casting, high pressure die casting. This uses heavy machinery and intricate dies to manufacture intricate parts, usually made by aluminium magnesium alloys. The basic challenge that we face in this paper is to automatically detect surface defects that appear in such parts, defects which might be unfilled regions, or might be cracks, or they might be shrinkages or other types of defects, according to a comprehensive list that NADCA, North American Die Casting Association, has compiled. The approaches that are usually followed in the last decade, I would say, concern matching techniques with comparison of the actual with the ideal surface, predetermined, predefined types of defects, and the tools that are used start with machine vision, of course, because we need computer images, pattern recognition, and recently artificial intelligence through neural networks, convolutional neural networks, support vector machines, and in our research, the main aim was to automatically determine if a part is defective or not, based on computer images, but we did not focus on determination of the type of defect. That's a future step. The research tasks that we are concerned with is first to acquire an adequate number of images to work with suitable quality, of course, and with immunity to light variations. Second task is to apply suitable image analysis metrics or features that uniquely characterize images of the parts, ensuring that these metrics are enough to differentiate defective from healthy parts. And then apply AI techniques in order to learn patterns of features in order to finally classify the parts as defective or not. In actual fact, we did a comparison between support vector machines and artificial neural networks. Research methodology starts with image acquisition. That's the first step. We used an automotive part about 230 by 210 by 10 millimeters thickness, made of aluminum, magnesium, and silicate alloy, AC 51500. We acquired 52 parts which were photographed. 15 of them had no defects, 37 had defects, cracks, stains, shrinkages, unfilled regions. You can see an assortment here. And we used for photographing them a camera of 8 megapixels, about 2.5 pixels per millimeter resolution. We constructed a smart jig that holds the part in place and somehow stabilizes lighting by isolating the ambient light. We used an illumination panel of LEDs and color temperature about exactly actually 4500 Kelvin, and we did some image pre-processing, transforming the image to acquire the same position and orientation for all images, converting to grayscale, enhancing contrast, sharpening, and removing the background by standard image processing routines in MATLAB. We did some further image processing in MATLAB. We were lucky enough because all defects appear and are expected to appear at particular regions of the part. So in particular areas, the regions of interest were defined like that by using the standard descriptor vectors, so-called surf descriptor vectors, by which pixels are placed and then boxes are defined. The box coordinates are extracted automatically, as you can see in this picture. Then in the regions of interest, in the images of ROIs, we had to do some noise elimination because the edges of the part that belong to regions of interest may resemble to defects, so we had to remove them. You can see in this picture at the left hand side the edges that appear blurring somehow the profile, and to the right hand side you can see the same thing after removal of these edges. So in order to do that, we applied binary masks suitably defined, then we filtered dark pixels. The threshold for filtering was defined by trial and error. Then we had also to perform some edge detection in regions of interest because we needed that these alternative images together with the grayscale images to extract features. And these features are the main characteristic of images. So we represent essentially images by these features. And what are these features? They are calculated, as I will define them next, and considered for all the regions of interest in each image of a part. So they are we consider all regions of interest in a part, and these features are the mean and the standard deviation of the brightness of all pixels, f1 and f2 we call these features, the mean and standard deviation of the brightness gradient, f3 and f4, these are these features, then the number of pixels and their mean brightness provided that the brightness is lower than a threshold, so that's a constraint. We need that as well. It's a different perspective. So a new couple of features, F5 and F6. Feature F7, which is the number of white pixels that are counted in pictures, in images derived from edge detection, as I described before, and then a composite, you would say, feature F8, which is defined as I wrote here, mean and standard deviation for brightness over mean and standard deviation for brightness gradient. Each of these features can be represented for all the parts that we tested by their numerical values following curves. You can see the blue curve here corresponding to a normal part and the red curve for a defective part. So it's clear that the normal part is represented by a curve which is well or mostly above the red curve. This is true for most of or all of the other features, and this is important because like that we can differentiate right from the start between good and defective parts. You can see the curves for all the rest features. Now the final part of our research methodology was part classification, so we used support vector machines and artificial neural networks. We use support vector machines because they are typically benchmark classifiers. We used MATLAB to construct the support vector machine for this particular application. We used cross-validation of 5 sets and the normalized input value ranges for 2 cases, one considering just 5 of the features and another one considering 7 of the features. This is an image representing the different combinations, basically, of the values of these features. In the first case, S1, in the second case, S2. Now, artificial neural networks, we defined them because we needed an alternative to support vector machines. This alternative concerns pattern recognition, supervised learning. We used MATLAB again to construct the artificial neural networks in this case. We confined ourselves to 1 or 2 hidden layers with a number of neurons ranging from 20 to 60. We used sigmoid activation function, 2 output neurons for the class and the probability of the part, defect or good, and the probability at which we can say that the part is defective or healthy. And then we use different alternative inputs combining different features. So we use different combination of features in order to see which combination gives best results. Out of the data that were available, 70% of them we used for training and 15% for validation and also 15% for testing. We chose the best architectures based on positive recognition rates and the avoidance of overfitting. So 4 of them emerged as the best. All of them had 1 hidden layer with 30 neurons, and the features that each architecture used as inputs were the ones that you can see here. So from 4 features, 5 features, or 7 features in 2 architecture cases. Results. Support vector machines gave positive recognition rates of 90% and 94%, which was quite good, not excellent, but quite good, taking into account that the parts were, the number of parts that we used was not that high. Artificial neural networks gave better results. You would say one of them gave 84% classification success rate, A2, and the best one gave 98% classification success rate. And this is an image of confusion matrices for A1 for this best network that gave 98% of success. Now, we made a trick. We combined all 4 artificial neural networks in order to have an ensemble result for robustness because of the small data set, and taking into account that the separation of the training, validation, testing sets is random. That is, a part that belongs to the training set for the first neural network might belong to the validation set of the second one, or the testing set of the third one, and so on and so forth. That gives robustness. The output of the ensemble classification is defined like this. So it's accuracy multiplied by classification for each of the neural networks summed up, and then the mean of that is the classification result. In that way, we compensated for cases of false classification. For example, in this case, the third neural network classified the part as normal, whereas the other 3 networks classified it as defective, and the ensemble result gave the right classification as a defective part. So what are the conclusions? The conclusions are, first, that the number of parts used for machine learning was small, of course, but this is expected. It's a problem in manufacturing applications. The robustness that we achieved is adequate, I would say, and we did that basically by smart designing of the work holding jig, which catered for relatively stable lighting conditions, which is a very important thing in machine vision applications. Now, neural networks were superior to support vector machines, judging by performance, flexibility, and robustness. And the small size of available data was dealt with by exploiting the ensemble of all 4 good artificial neural networks that we derived. Future steps: augmenting, of course, the dataset and retraining the networks, and a more ambitious aim to identify and classify individual defects by considering labeling of regions of interest or some grouping of them according to guidance by by the experts, I would say. And the experts were Viral SA, which is a high-pressure die casting company in Greece, which we gratefully acknowledge for providing consultation. And of course, I'm available for questions and your discussion, perhaps. Thank you very much.
Dear esteemed colleagues, my name is Vasily Larshin. I represent Odessa city in Ukraine. I also represent 4 authors from different Ukrainian organizations. The first, State University Odessa Polytechnic. The second, Odessa Military Academy. And the third, Odessa State Agrarian University. All 4 of us have prepared this presentation, and I am entrusted to present it. The topic of this presentation is discontinuous generating de-grinding optimization. Now let's move on to the next slide, number 2. This slide number 2 shows introduction and major challenges. There are 2 de-grinding methods: profile de-grinding and generating de-grinding, with 2 D-shaped wheels. You can see the corresponding figures. Now let's move on to the next slide, number 3. This is generating de-grinding with 2 D-shaped grinding wheels. The first, the involute is traced by an imaginary point at the end of the beam. Second, the de-grinding high accuracy is due to the fact that the conical concave cutting surface of the wheels occupies a constant axial position. And the last, there is no grinding fluid. Now let's move on to the next slide. Slide number 4. This slide shows aim and research task. The research aims to develop a de-grinding hierarchical 2-level control system when the first control level is Z at the stage of pre-production, and the second level is the robust automatic deviation control system that stabilizes the optimal operation conditions found at the first level. So, this is the research aim and research tasks. The first task: create and research a de-grinding optimization model. The second, calculate the optimal distribution of the de-grinding stock allowance and de-grinding power along the grinding strokes. And the third, develop a robust automatic deviation control system that stabilizes the optimal operation conditions. And the last, show that de-grinding optimization at the control hierarchy upper level is a method of de-grinding operation design, while at the control hierarchy lower level is a control method. Now let's move on to the next slide. Number 6. This is research methodology. The grinding power can be obtained experimentally in the form of 2 formulas, number 1 and number 2, where C, X, Y, Z are the coefficients that depend on the angle of dish grinding wheels installation. T, V, N are the depths of cut in millimeters, longitudinal feet in millimeter divided by minute, and G swings N. There are several designations, and then the formula is obtained for total machine grinding time, and this is also the objective function. Now let's move on to the next slide. 7. This is constraint on the defective layer depth. On the left, you can see the figure, the dependence of defective layer depth on the GI grinding power. It's indicated the following: 15 and 0 degrees are the grinding dish wheels installation angles. 1, 2, and 3 the materials to be ground. Hence, the following equation may be obtained for defective layer depth. Formula number 4. Let's move on to the next 8. This is optimization mathematical model. You can see the corresponding formulas. In particular, after substituting these equations on the left into equation for tau with index m, we get the total machine grinding time, tau m, spent on n working strokes. This is the sum of 4 components, and you can see the formula for objective functions. Now let's move on to the next slide. Slide number 9. This is methodological approach. You can see on the right the figure that shows hierarchical control with 2 levels. Upper control level or optimization as a process design method at the pre-production stage, and lower control level optimization as a process control method at the production stage. Now let's move on to the next slide. Number 10 shows results. On the left you can see the figure. On the right some designations. This is the objective function special case when n equals 2. To prove the unimodal nature of the objective function tau m, let's consider the case n z is equal to. For this equation, for grinding machine, we have the following formula. Now let's move on to the next slide. Number 11. This is special case and the corresponding results. You can see the table and you can see the figure on the right. Okay. This is a case when n equals 2. You can see the table for different grinding stock allowance, and on the right of the slide you can see the figure. So the derivative of the function tau by the parameter of the grinding depth for the first stroke you can see. Then the derivative equals 0 and the grinding depth for the first stroke may be obtained. Now next slide. Next slide, number 12. Upper level control system. 2 stages of the optimization. First stage. For a specific amount of grinding stock allowance Z, determining the optimal number of G-grinding working strokes N. This is structural optimization. And second, knowing N, determining the optimal grinding depth for each of these strokes. Parametric optimization. Figure shows a solution of the first mentioned stage. Now, next slide. Number 13. This slide shows lower level control system. On the left, you can see experimental data. This is G grinding power automatic stabilizing. On the right, you can see robust automatic regulation system with several blocks. Now, next slide. Slide 14. Slide number 14 shows conclusions. The first, the developed optimization model made it possible to control the G grinding operation at the upper level of the control hierarchy. That is, at the pre-production stage. Second, the optimal G grinding parameters found by optimization, G grinding depth and power at each working stroke can be used as input data for controlling the G grinding operation at the production stage. And the last, the procedure for G grinding optimizing at the pre-production stage is a method of designing of G grinding operation, while at the production stage, it's a method of controlling this operation. So, next, number 15 shows future grinding system research methodology. There are several blocks: modeling, optimization, and controlling. Optimization as a designing method, and optimization and controlling method. Controlling contains direct and indirect directions. Now, next slide 16. This is acknowledgement. This work is carried out in accordance with the state Ukrainian budget theme of the Odessa Polytechnic National University. And the second, this work is continuation of the cycle of scientific research initiated at the Scientific School of Professor Alexander Vasilyevich Yakimov in the field of technology and automation of grinding of hard-to-machine materials. Next, number 17. This is the last slide. Thank you very much. My characteristics is given below. Once again, thank you very much for your attention. I am ready for your questions.
Good afternoon. My name is Ruslan Jumaledinov. I am a lecturer at the Department of Mechanical Engineering of the Crimean Engineering and Pedagogical University. The theme of our research is ensuring the quality of conical mating surfaces processing by diamond honing. The need for the development and improvement of technological methods of machining parts arises due to the high requirements for the quality of products of mechanical engineering production. The use of the synthetic diamonds as elements of cutting tools in finishing operation, one of which is honing, allows with the less material movement to most intensively influence the surfaces to be treated and control the microgeometry and physical states of the surface layers. The processing Technology of internal and external precision mating cylindrical surfaces does not cause problem. At the same time, the connection of precise conical surfaces is difficult due to the processor errors of conical holes. The research aim is study to improve the quality of processing of conical holes by diamond honing based on the mechanics of the contact interaction of the tools with the workpiece based on the theory of elastic plastic contact. The contact pressure were recorded using strain gauge glued along the generator of the workpiece additional supports and introduced into the design of the proposed block. The position of these supports can change the nature of the conical load depending on the tapered angle of the hole being machined. The result of experimenting using an industrial blocks shows that the change in the contact pressure along the length of the stone is within 1.04 to 0.07 megapascals. The proposed construction of the block made it possible to reduce the contact pressure along the length of the stone. Measurements of the deviation from roundness after finishing boring, honing with industrial and offered tools have been carried out. Comparative analysis of the data shows that the alignment of contact loads when using the proposed tools provides a significant reduction in the deviation from roundness. The strengths of the generatrix of the conical holes were determined in two mutually perpendicular longitudinal sections after processing with industrial and proposed blocks. The data obtained shows that after honing with stone 500-400, strength deviation was from 28 to 103 micrometers. With the industrial block and from 11 to 58 micrometers with the proposed block, and with stone 125-100 respectively from 32 to 95 micrometers and from 6 to 52 micrometers. That is, an orange to fault strength correction was obtained. According to the results of given data, the depends of the correction factor along the length of the generatrix of the conical hole after 1 minute of honing is plotted. The correction factors depends on the initial shape of the tapered hole obtained during the preliminary operation. We can conclude that negative values of correction factor are associated with the fact that the machine honing time was 1 minute. This time is not enough to correct the errors of the preliminary operation, the maximum values of which took place in the area of the small holes of the cone. The nature of the graph shows the equivalence of the correction factor along the generatrix of the conical hole when using the proposed block, which depends on the distribution of contact pressures. In the process of honing tapered holes and thus tool movements from small to large bow of the taper, the width of contact of the bow with the machined surfaces decreases. At the same time, the number of cutting grains also decreases, which leads to their deeper penetration into the work surfaces. Therefore, the study of the depths of penetration of cutting grains is of great importance in solving the problem of improving the quality processing. Based on the data obtained, graphical depends on the depths of penetration of cutting grains along the length of the generatrix of the conical holes were plotted. The graph shows that the depths of penetration of the cutting grains of the diamond bar into the work surface. It should be noted that when using an industrial block, the depth of the grain penetration is the range of 1.2 divided 9.7 micrometers, and with the proposed block from 1 to 5.7 micrometers. The decrease in the penetration depth of the grains at the larger hole is due to the fact that the introduction of the additional supports, an optimal location of which was determined experimentally, level to the contact pressures. Analysis of the honing processing using the industrial block showed that the processing proceeded with uneven material removal. This is due to a change in the load acting on the working surfaces of the bar when moving along the generatrix of the conical hole. This leads to a deviation in shaping and decrease in the surface's quality of the tapered bore. The studies carried out characterizing the surface quality during honing of tapered hole showed that the deviation from roundness decreased by 1.7 times, the strain deviation decreased by 1.8 times, taper angle deviation decreased 1.6 times, the penetration depth of cutting grains along the generatrix of the conical holes was from 0.97 to 5.7 micrometers. Thank you very much for your attention.
My congratulations, dear friends. My name is Anatoly Tkachuk. I work in Lutsk National Technical University, Ukraine. Research on the topic is offered to your attention influence of turning operation of waviness, characteristic of working surface of rolling bearings, introduction and major challenges. Machining of parts takes place using machining operations which provide the initial and finishing processing to varying degrees affect the final formation of the geometric characteristic of the functional surface. If the ratio x divide n integer, x is the ratio of the frequency of harmonic oscillation of the tool of the workpiece, and its frequency of rotation of the spindle. The harmonics oscillation does not affect the shape of the longitudinal section of the part. In order to prove the technological heritage of the waviness, it is necessary to establish the relationship between the processing modes and the microgeometry of the functional surface of bearing rings. Moreover, heritage is machining not only in the finishing operation. It also occurs during the operation in the bearing in the product because of external factors of operation conditions. The formation of the waviness of the functional surface bearing is a provision operation at the macrogeometric parameters of the structure format, and its appearance can be observed in the finishing operation. In this figure, you can see hereditary nature of origin of the waviness. A. It's round diagram of the rings raceway after turning operation, and B, it's a polar diagram for the rings raceway after grinding operation. Aim and research tasks. The aim of the study is to improve to technological of formation surface of rotation of the roller lines of automatic turning operation to stabilize the parameter of the geometric structure of the surface and the performance properties to roller bearings. Research task. First, identify the main causes of shape deviation and determine the technological methods of controlling the waviness of the structure of rotation in automatic turning operation of the formation rolling tracks of lines. Next, develop a mathematical model of dynamic of the formation surface of rotation on automatic leisure to control the parameters of the geometric structure of the surface. And next, to develop engineering methods of technological control and amplitude and step parameters for the waviness of working surface of lines of multi-tool turning and automatic operation of condition bearing production. Research methodology. During the rotation of inner rings of the bearing, the simulation interaction of the deviations of the rolling surface of both lines and the rolling elements case oscillation of the our lines of the bearing its vibration. A complex periodic function describes the displacement of the our lines in the form of Fourier series, which consists of simple harmonics oscillation which frequency multiples of the fundamental. At the harmonics amplitude decrease the contours shape approaches of the base circle, and deviations the detected in the cut of the contour, but the number of faces corresponding to the number of the harmonics. In the figure you can see contour shape corresponding the third, fourth, and 5 harmonics of a periodical function which period 2p Fourier series for 0 initial shapes and small amplitudes. Vibroacoustic characteristics of the bearing determinate when the number of waves of the K harmonics on the tracks of the inner of outer lines with the number of bodies of rotation in the bearing. If K equal QZ, where Fk is the number of waves of the main harmonics in the track. Spectral analysis methods were used to diagnose cases of technological defects of bearings. The spectrum allowed use to identify predominant harmonics which are present in the schedule of the series and depend of number of rolling elements. In this figure you can see tolerance of the harmonics of the spectrum on the bearing line the number of rolling elements that equal 20. That equal 20 in this harmonics. The micro relief step parameters depend of the ratio between on longitudinal and traverse feet and the workpiece rotation speed. Therefore, the formation of vibroacoustic characteristic of the functional surface of friction pace largely depends on the functional features on the technological equipment. In this slide we can see the calculate scheme of the spindle machine. Next, its designation used for this mathematical modeling, and we can see formula describe the equation of oscillation of the masses dynamic spindle system in the corresponding direction of rotation. Results. In the course of research works depending of waviness on processing parameters at various frequency of rotation of spindle were established. Theoretical study have been confirmed experimentally which 15-20% errors. Graphs of dependence of the amplitude of oscillation of the cutting tool during the processing of lines of bearings on the spindle speed build. In this slide you can see dependence of the amplitude of trans oscillation of the machine spindle speed and dependence of amplitude of longitudinal oscillation in the spindle speed. This figure shows the formation of the waviness of functional surface of parts such body of rotation, considered theoretical calculation and the approximation which experimental studies to confirm the oscillation of the forming system of the machine, which significantly affects the formation of operation of waviness roller bearings. In the next slide, research results are realized in the form for engineering methods to design tool adjustment of leisure which subunit of adjustment waviness at the stage of determining the forming modes. The design of a contours billet of a set of two lines roller bearings is offered. The structure of technological process of manufacturing rings change. Found of the waviness the functional surface operation during which operation take from obtained during processing in the initial operation, including turning. It's can see a working surface of roller bearing ring after operation turning. In this slide we can see next information. Due to the introduction of the proposed design of the workpiece, it was possible allowing systematic defects in the turning of the outer lines associated with the formation of the clamping elements of the spindle chucks. The engineering technologies of adjustment leisure in the conditions during production approach the machine to optimize the machine's productivity, the change of structure, technological process of manufacturing lines of roller bearings. This allows us to optimal cutting modes for tool which different values the periodical stability. An algorithm for automated design of structure and parameters of tool adjustment of leisure was developed, which allowed precising the optimal parameters of waviness at the stage of technological design. The structure of this algorithm we can show on this slide. And conclusions. The waviness and deviations of the shape of working surface of the line, the heredity, they begins procurement 10-15%, transformation into mold 40-55%, head treatment 10-15%, and operation finally format of the final operation of rounding and finishing 20-25%. The control of the waviness and accuracy of the working surface of bearing grinds must be carried the life cycle of the lines, starting from the workpiece tuning, shaping operation, and final grinding. The lining case of waviness and deviation of the shape of the turning surface of bearing grinds, implementation of the workpiece and forming process, the presence of procedural deformings from clamping elements of machine, dynamics oscillation of forming elements of machines, device and tools, the step parameters of the critical harmonics reply are related the ratio between and workpiece rotation frequency and oscillation of the forming instruments and amplitude parameters, which the amplitude of the oscillation motion. This at the ratio 1/2, the workpiece rotation frequency N and tool oscillation frequency K. The shape deviations is close of the oval one. At the ratio 1/6, the shape deviation in close in the hexagonal one. The waviness of the 11 harmonics results 12. The waviness of 12 harmonics results from the frequency ratio 1/12. Conclusions 3. For preventing technological defects during formation of the lines working surface is necessary to allowing exceeding the specified tolerance of waviness machining equal to the multiplies number of body of rotation in bearing. The harmonics of waviness should dominant considered by H1 divide equal H1 equal Z plus or minus 4, H2 equal z plus or minus 3, H3 equal z plus or minus 4, H4 equal z plus or minus 5, where z is number of bodies of rotation in bearing. It is planned of a field tolerance of the dynamic waviness of ring working surface for spectrum harmonics from 0 to 500 depending on the ratios of bodies bearings, rotation and waviness. This will make it possible to optimize the limit of economically fusion values of vibration, velocities of critical harmonics, and hence of the replace amplitude which specifies spectrums. And acknowledgement. The research was partially supported by International Association for Technological Development and Innovation. Our team is very grateful for that. Thank you very much for your attention.
Our stream is over. Therefore, try to our question. If I know that everybody from reporter exists here, except said report, the author for this report from Crimea, and we have problems with connection with Crimea because Alper from Turkey now is on another make a report on another session and can't connect to us, and from Crimea this connection is blocked from the Russia, unfortunately. And
the main issue, Crimea is Ukraine, and this is the main issue for this.
Yeah, this is a part of Ukraine, of course, but this we have problems with connection, unfortunately, from our friends from Ukrainian citizen with Crimea. You know about this.
Please start from the first presentation that was surface defects.
First presentation from our friends from Greece. Have you some question for reporter? First of all, I'd like to say it's very interesting report, and I propose for you the cooperation, because the idea which you report during this your study is very simplicity for our for works research work of our department. In future, I propose for you this cooperation, I hope. And can you explain the connection between the stage of improvement of control and improvement of planning of structure and parameters of
of these properties. Influence defects to the operational properties. Do you understand?
Yes, thank you very much, Mr. Chairman. The defects are, at the moment, at least the research effort was to identify defects. There was no attempt to connect defects with the casting parameters. That's a later stage, definitely. And also there is another stage before that to identify particular types of defects, because if you noticed, what we needed to do in the first place was to identify whether a part is defective or not. Not the type of defect, but just if the part is defective or not defective. And we did that because the company which sponsored our research, DRL, wanted to automate quality control. So in quality control, what they were mostly interested in was to not send to the customer defective parts. They were not really interested to see what type of defect that was. So long as there was a defect, they would not send the part to the customer. They would just scrap it. They would remelt the part and use the material in the next casting batch. So initially, what they wanted to do was to automate this quality control. Now, because they want to improve the casting process, it would be very interesting to automatically identify the type of defect and then relate it to the process parameters, which is quite easy to do because all high-pressure die casting presses are PLC controlled, and all casting parameters are available online. So it's possible to record the history of process parameters, and since we would have the history of defects, what type of defects is identified, the connection, especially using machine learning techniques, is straightforward. So the next future step, the immediate future step, is to make that connection.
Thank you. Really, a lot of questions, a lot of proposition, a lot of interesting ideas about this, and we can to have a great time for this discussion. And I hope that our discussion, our cooperation will be more and more interesting, because really it's very interesting for us. Thank you for.
Thanks very much, and I'm available for any suggestions.
Dear colleagues, Professor Derevyanchenko, Odessa Polytechnic University. Our report was demonstrated. Why, Vitaly Alexander? We send our report. What is the problem with this?
Professor Derevyanchenko, it's
if I understand, this report will be ready for presentation. Yes.
Yes, as it will be ready for broadcasting, we will broadcast it. Due to technical reasons, we just continue on discussion, but we come back to your presentation.
Okay, we are ready.
Thank you.
We'll wait.
If this presentation will be ready, we'll continue. And another, it was a presentation from Professor Larsen, isn't it? Second, sorry, I closed my book, and therefore.
Yes, it's correct. Report with the title "Discontinuous Generating Geo-Gradient Optimization Delivered by."
Yes, this is a geo-gradient optimization. Professor Larsen.
I hear you. Do you hear me? Do you hear me?
Yes. I'd like to ask about the connection with the planning of structure and parameters of the grinding operation. Yes, and the operations of these gears. Do you understand? Do you understand the question?
Connection between grinding operation and what?
About parameters and structure of technological operation and future functional operation of this. Do you study this question?
Yes. It was found several grinding operations after optimization of this operation.
Optimization what? Structure or parameters?
Parameters. Structure the same. Structure is known. Its parameters were found. Parameters, grinding operation parameters. Parameters as a result of optimization. And then automatic regulation this operation. Parameters, not structure. Structure is well known. Structure of this operation is well known. It's necessary to find parameters of this operation. The number of strokes, the cutting depth, and so on. Do you understand?
And what criterion of this optimization?
Criterion is objective function. This is a grinding time, machining time, grinding time in minutes.
Sure that just the time for machining is great criterion, the best criterion, maybe a cost, maybe
cost, but this is grinding time, grinding machining time in minutes, not in cost.
Let it be. Okay.
This is objective function of this operation.
And this limitation will be, and limitation for this optimization is
yes, there's several limitation of this operation. For example, defective layer depths. Defective layer depths after grinding. Defective layer depths.
And did you find analytical connection with the great parameters of operation?
Yes, it was found the dependence between defective layer depth and the cutting parameters. This is experimental dependence, not theoretical. Experimental.
But if we change the parameters for all your research or your experiment will be changed, isn't it? Let's go. This is only discussion, and thank you. Have you another question for this report? Maybe somebody wants to ask some question. Thank you, Vasily. I'm very glad to see you, really.
I'm also very glad to see you.
Yes, if you have...
do you remember Natasha Lishenko? Do you remember?
Of course, sure.
Now Natasha Lishenko in Dublin.
Dublin, yeah.
Dublin, in great university.
Let it be. We'll wait here in Ukraine. That's well. If I said that set report we can't to ask to question because nobody here with some problems with connection. Question because there is blocked nobody from here, Russia. With some problems with connection. Question because there is blocked nobody from here, Russia. With some problems with connection. Question because there is blocked nobody from here, Russia. With some problems with connection. Question because there is blocked nobody from Russia. With some problems with connection. Question because there is blocked nobody from Russia. With some problems with connection. Question because there is blocked nobody from Russia. Unfortunately, we have some problems with connection. Question because there is blocked nobody from Russia. Unfortunately, we have some problems. The next report, the influence of turning operation of waveness characteristic in working surface in rolling bearings. I want to ask for you, really a turning operation, this is a Rauch operation usually, yes, isn't it?
Yes, turning operation formatted waveness in track Rhines rolling bearing.
But you said about influence for the operation characteristic of bearing. Bearing, this is a very study object. Yes, of course, but a lot of finishing and super finishing operation after turning. Yes, isn't it? Yes.
Yes.
Are you sure? And you said about only for influence just on turning operation. What is the connection with the structure or parameters of turning operation and the future properties of bearings?
The main results of the study is a blank is form of tower which allowed a created of technology of selective assembly and control manufacturing of waveness. He turning of two lines and is carried out for one technological basis. And last, the workpiece tower is cut in the middle of a ledger, and we get workpiece of the first and second lines. This technology has been included in introduced into production SKF Ukraine in city Lutsk.
You said about inheritance? Maybe inheritance just this very interesting property. This is inheritance from raw operation to the finished operation and for the future or operational properties of bearings rings or another part.
Yes, it is.
Let it be. And I'd like to ask for you. You said about scheme for machining, yes, and you said only about the damping connections without the staffless connection. The usual, the many well-known scheme use staffless same as damping. Yes, connections.
Yes.
And you said only about damping, and therefore you can't to explain the process appear this waviness, maybe roundness, a little bit. Unfortunately, I don't understand this scheme. Maybe you try to explain for you for this scheme. let it be. Maybe this is a discuss. Maybe I didn't something to this idea for this, but result experimental result said that your ideas was correct, and therefore you have to think about this, because usually, yes. Vasily Larsen, is did the all dynamics scheme use same as status as damping connections?
It's me. It's me. Vadim, what is your question? To whom?
I said that every dynamics scheme, every dynamics layout use as damping, as stiffness connections from another bodies of tool machines, from spindle, from tool holder, from workpiece.
Let's move this question to discussions in offline mode.
Maybe this is a discussion, not question, but discussion. You may
Thank you
to think about this, because this is a really not mistake, but maybe problems with this.
Thank you very much. We will take this in account later.
Okay.
A new method for the monitoring cutter states in finishing turning of hard materials. Introduction and major challenge. Between reasons which are preventing the introduction of new technologies, take place various types of technical system failures. The need to create new methods for monitoring the cutting tools state is obvious. Cutting finishing is an essential element of modern technologies. Preliminary researches of authors showed that in the conditions of finishing turning of hard materials, take place forming a number of cutter-specific defects. They are reduce the quality of processing and the resource of tool. Aim of research tasks. The research aim is development of new methods for monitoring cutter states in finishing turning of hard materials. This method must make the possibility to detect a complex of defects in the tool cutting part, which appeared as a result of its wear and making tool adjusting. Research tasks. Identify the main types of cutter defects that occur during finishing turning of hard materials and conduct their research. Develop and explore ways to identify the features of these defects in the respective state spaces. Determine the main method for recognizing class of cutter defects. Investigate the buckling effect in the finishing turning process due to the significant changes in the geometry of the cutting edge as a result of cutter wearing. Research methodology. On this slide is presented a scheme of smart system for cutting tool state estimation, which authors were used in according experiments. The experimental research was carried out under condition of processing hardening steel on the laser model TPC-125BH1P. Material of cutting tool composite 01. Cutting condition is presented in the cutting speed, depth of cut, and feed rate diapason changing. In position A are presented the photo of stand which was used in experiments. At position B are presented the digital images of varying zones of laser. Let us discuss the block scheme of digital image processing. Digital image pretreatment model for cutting to via zones. The model for contours of macro and micro cutting part defects highlighting. The model for the formation of via zone primary and secondary signs. The model for reducing dimension of the signs space of via zones with genetic algorithm using. The model for the image selection of via zone texture. The model of classifier of defects from the cutting part via zones. The model of recognizing of cutting part state of one cutting tool. The model of prediction of the residual life of the cutting tool. General form of laboratory standpoint comparison result of using a smart system and stand create of the base of profile. Monitoring result with smart system using and laboratory stand. Results divergence did not exceed 5 or 7%. Results. Generalized results processing scheme is present on this slide. Position A, B, C displays the process of cutting edge process projection combining. Block for formation of cutting tool adjusting on the value of radial viewer HR is present is position B. Let us discuss the main blocks. The blocks for formation and analyzing the of section of cutting ray and calculation the necessary correction the feed value. Block for estimation the state of flank face, estimate the distance from the extreme groove to the top, calculate the necessary termination of processing. Block for formation of cutting tool adjusting on the value radial view. Block for formation correction taking into account changing noise radius. A demonstration of buckling effect of finishing turning process is shown at slides 12 setting. The coding graph constructed using a special grid and release software. To avoid such situation in finishing turning process, a special algorithm has been developed. Demonstrations have allowed to achieve cutting stability by one uncut finishing tape. There is A, the zone of two combined cut edge projection, displaced on S value. 3 and 4 zone where take place relation A less than A minimum. 0 zones. 5 and 6 example according chips. 7 and 9 example according zone of treatment. B. Sweeps of the cut layer 10. The cutting edge state is recognized as a failure state due to the loss of cutting stability. The cut of chip have an intermittent character. In some parts of the cutting edge, cutting does not occur. Schema of building sweeps of cut layer for different value of cutting thickness. Operation C1 and C2 means the AT increasing. Position D and E demonstrated the chip type in zone where take place release. A is less than A minimum. Example of graphs showing cut section during finishing turn with a new onboard cutter are present on this slide. Formation, the set of the features of varying flank face, form and cut state recognizing. Example of make decision process about possibility of instrument further exploitation is presented at this slide. The main stage of digital image processing and flank face variant are presented in there. The right side of the figure shows the model for recognizing the class of real zone shape and making a decision on the possibility of further operation of cutters. Conclusion. The specific defect of cutter for finishing turning cutting part when processing the hard material due to real according systematization has been carried out was identified for the text group. As a result of research is created new method for monitoring cutter states in finish turning of hard materials and recognize name defects. Method realized with a special smart monitoring system. Done identification the main type of cutter defects that occur during finishing turning of hard materials and conducted their research. Developed and explored ways to identify the features of these defects in the respective state space. Determine the main method for recognizing classes of cutter defects. Combined recognition method based on the successive application of the method of statistical decision and stochastic approximation. New method for monitoring cutter states in finishing turning of hard materials by author opinion will allow to increase the quality and the resource of tools in finishing turning. Acknowledgement. The author expressed their deep gratitude to Mr. Evgeny Shoin, who took part in developing the algorithm and software for determining areas where the cutting thickness is less than the minimum allowable. Thank you very much for your attention.
You said about the new approach for recognition the defects. Yes, try to explain for me what type of this method. Maybe optical, maybe loading, maybe another. A lot of different methods exist for understanding the varying the defects, different defects. And you said about what?
Yes, Vadim, I understand your question. As slide number 10, there is smart system.
I don't want to explanation.
Okay.
Explanation. You said about
we using optical method.
Optical.
With digital camera, which can register the digital image of varying zone of cutters, and after that, with smart system algorithm, we process the digital image the results of this we are using for recognize the cutting to state.
Well, it's very optical method is very difficult because complicated because the environment, machine environment is very closed, and this is
yes
fast. And another question, if you can claim for me. Firstly, you said about only wear of length surface, or maybe rake surface, maybe radius of edge.
Yes.
And what are the most important characteristic which you propose for analyze for making the better residual life of your tool?
We try
length face or surface or flanks or maybe a rake face or radius. No radius maybe.
In our method, we try to recognize the states of different zones of varying colors.
Yes, this is a complex parameter.
Yes, of course.
For complex parameter, we need to unite this. The united is for me it's too difficult, but this is a very interesting task. Therefore, another question.
I have a question. Do you hear me?
Yes, of course.
Yes.
I have a question. Tell me, please, who is showing? Where does he work?
He is my student. We working them some years ago, but he is not live in our country, and I have not contact with him. But he take part in the algorithm and software. So we make a gratitude for this attention in this process.
Okay, thank you.
This is a review report. First of all, a review, and there are more and more questions for all ideas, because to explain during the one report is too complicated here. That's well. Thank you for everybody for your interest in the reports. I think the main aim of our conference to find new ideas, new connection, new cooperations. This is more interesting, more exactly more. To find together cooperation. This is more interesting than the results, isn't it? Yes, Vitaly.
Yeah.
And therefore, I thank you for everybody. First of all, to our foreign participants of our conference, because in so hard time for Ukraine, they find possibilities to connect with to other conference, and I'm sure that the next conference will be in Ukraine. It will be in our love Sumy city. And thank you for Vitaly Vadov for these possibilities to see our friends and to discuss with scientific problems with our conference. Thank you very much.
Thank you very much to Professor Stopnitsky. I definitely agree with you, because the main idea is a platform for communication where we can exchange our ideas, share our recent results, and online is good when we can connect from different countries, but offline is better. It's true. Thank you very much, Professor Stupnitsky, for your
Thank you.
commitment as a session chair. Thank you very much to all participants for your questions, for your contributions. And today's agenda is completed. See you tomorrow. I invite you to join us in Virtual Hall D. We are planning 2 sessions for materials engineering and 1 session ICT for engineering education. It will be interesting. See you tomorrow. Thank you
See you tomorrow. Slava Ukraini.
Thank you very much.
Thank you very much. Thank you.
See you.